Hi, I'm Brian Pavlakovic, the Technical Director at Guide Ultrasonics. I'm going to be talking to you about the QSR Scanning System, showing you the products and how we go and use them. So we're going to look at both the Circumferential and the Axial today. So let's get started. This is the QSR1 system. This is the electronics pod. We call it the E-pod. It's actually used both with the Circumferential and with the Axial. And it goes and collects all the data, digitizes it, sends it to a PC where it can be analyzed. We have frames which are size specific to the diameter of the pipe, allows us to put everything in place, hold it on the pipe, and lets the system know what size pipe it's actually testing so that it can help configure itself. So these are 8-inch frames. We're going to be testing an 8-inch pipe today. The circumferential system can do from 6-inch to 24-inch, and all those frames can be purchased or provided. The system has 2 sensors. We have a receiver, which is this one here. And we have a transmitter. Whenever we pack them, we keep the flux keepers on. And with the flux keepers, the magnetic field is low enough outside the box that it can actually be shipped as non-magnetic material. So therefore, it's safe to fly with. Go and lock these in place. After that, we're ready to go and test. Let's go to our pipe. Now, QSR1 uses the same eye button system that the wave maker uses. So we can go and recognize the inspector if you want to go and do that. Just adds extra stuff to QA. It does collect without the eye button, but this helps you validate that everyone has done their training, knows what they're doing, and you can get the quality results out of it. Let's connect it up to the PC. We're going to be using USB for this demo, but it also works with a LAN connection. That allows you up to 50 meters. But when you're close to the pipe, USB actually ends up being simpler. We'll go here on the Wave Pro QSR software. It's able to go and recognize the instrument, recognize what sensors it is. Now we're just ready to collect. Press the auto configure button. It's then going to go and ask what pipe we're testing. We can go and give it a reference designator, so then we can go and help our reporting later. We know where it's from. Also, the unit itself has a GPS built into it, so we know where it's coming from, where it's at, again, to help reporting, to make everything as easy as possible for the inspector later. Now, this set of circumferential sensors can do from 1/4-inch to 1/2-inch pipe, or 1/2-inch thick pipe. That's 6 millimeters to 13 millimeters. And the system actually is now running through an auto configuration routine to determine what pipe thickness it is and how it wants to go and modify its magnets, how it wants to modify itself in order to get the best results on this particular pipe. So we don't have to manually change coils for different wall thicknesses. We don't have to go and change any frequency filters. The system's able to do it all. So in this particular case, it's found that it's a 6 millimeter thick pipe, which is correct, so it's a Schedule 20. And it's chosen some configuration parameters, so we can just tell it to do an auto scan. And we'll let that go and continue on. So we've chosen 1 centimeter steps, which is normally what we go and do. So what it does is it does a collection by sending from the one sensor, receiving on the other. The waves are going to go both around the top, and they're also going to go around the bottom. Okay. And then once it goes and collects enough data at that point, in order to go and be quantitative, it's then going to move on axially to the next point, and then it does the collection once again. And then it just goes and builds up these sort of slices in order to go and get our final result. Okay. So we can see on the plot here, we're going, each axial point is being added on. And then it's hard to see, but there's actually 2 different colors here. One is a dark black. That's the pipe thickness on the top half, the short section of the sensor. And then there's also a blue line. That's the average, the standard wall across the long path, which is normally the bottom of the pipe. Then whenever we go and hit an area that's reduced, the system can go and detect that. And it then shows that as this red line, which you can go and see starting to come in here. And this is now showing you the shape of the defect, telling you the minimum remaining wall at that axial location. And then once you go and build this up, once you have that minimum remaining wall, and we can see how far along it is, we're then able to go and put those values into any of your fitness purpose calculations or anything else you might want to go and do. We'll just let it scan for a little bit longer. Normally we go and scan from, the circumferential system was really designed to do simple supports. We know you have a support that might have some corrosion, it's looking a little bit rough, you see some corrosion product, but how deep is that? Is it something we need to go and deal with? Are we able to go and lift the pipe in order to go and to get rid of some of that corrosion product and actually go and mitigate the problem? Or is it actually too much loss for that? And so that's what this can go and tell you. How much wall is left, what is safe. So we normally scan from before the support, through the support, and after the support, and go and get a result. That should be enough data there, okay? Now, as we collect and as it goes and gets some preliminary results, which it goes and shows. However, we need to go and analyze these a little bit more because it's just a very crude system there. So there's two ways of doing this. Our new way, which we really go and recommend, is using our cloud-based assisted interpretation. So in order to do this, we simply go and export the result. Export the result. And then we go and bring that result onto the scanning studio, which allows us just to click and drag. It goes and gets uploaded to this. The scanning studio is based on a machine learning algorithm that's been fed with many site results. It's been fed with hundreds and hundreds of machine defects that represent realistic defects on site. We've then done a lot of finite element modeling for all those results to go and verify that our finite element modeling is correct. And then once we know that it's correct, we were able to simulate lots of other defects and run through all different parameters of different types of defects and shapes. And so all of that, millions of data points went into a training set. So it means that the assisted interpretation is allowed to go and take the information that is learned from millions and millions of defects and analyze it, as opposed to your normal inspector who's just been trained, who's probably only seen a few, tens or hundreds of results. And so it allows you to get really consistent result. And it also allows you to do it much more quickly. So you can just go and upload, wait 3 or 4 minutes, and you're going to go and get your results. You're not sitting there analyzing. But let's go and look, if you were to go and do it manually, what we go and do. So this is an example of the manual interpretation. We're looking at this plot at the bottom here, which we call the stars and comets plot. And actually what it is a representation of frequency versus time. And it has some wave modes on this frequency time show up as vertical lines. Those are what we're calling the stars. Those ones don't happen to be sensitive to wall thickness, but we're still using them to determine where the sensors are and how the system's behaving and calibrate the system. We then also have these long curving ones. These ones we tend to refer to as the comets. These ones are very sensitive to the wall thickness, and this is what we're really using to measure what the wall thickness is. Now, we tend to get them in pairs. So the first one here that you sort of see in magenta is marking what's affected by the short path. In this case, in most cases, the top of the pipe. The second one along, the second pair of a star and a comet, is the long path around the bottom. And then you get multiples of this as the energy continues to circle around the pipe. And this is the nice pattern that we go and get when we're on clean section of pipe. But then as we move along, we're going to start to see some changes in the defects. We're losing the bottom path. We're getting some reflections. And then as we get back onto good ones, our bottom path comes back together. Now, fortunately, the way we've set up the analysis and the way that we do with the comets, it's a frequency-based analysis primarily. And what this means is that dependent, it's not dependent on surface roughness. It's not dependent so much on attenuation. It's not dependent on how thick your coating is and how the coating changes as you go over something. We're able to determine how the comet changes as it goes through a given frequency by looking at those plots. And that then allows us to go and correlate that exactly to the remaining wall thickness that we had left. So we're able to get nice, reliable results both in the lab and on site. So we uploaded our data to the system. We now have it here. You can see our scan. So it's done the extra analysis for us. So we can go and we have a heading of the general information that we got from that pipe. We then also have a profile here of what the remaining wall thickness is and where the losses are. And it's then highlighting any area that's more than 15% wall loss. Okay. You can then add any comments you want to go and do. You can add any photos you want to go and add in. And then we can go and export this report. It can either be in a PDF format or you can go into Excel. Once it exports, you go and get the same information that you would want to go and have in a report. So we have the general header of where we went and did it. We then have a picture for the report. We then get all the information about the different thicknesses, the average thickness on the top section, the average thickness on the bottom section, and then the minimum remaining wall gets plotted everywhere. And so then that goes and allows us to go and see how the wall changes axially along the pipe without actually having to get to that bottom of the pipe. So if that's in a support, that's something that's corroded, that's on dirt, we're able to go and determine the minimum wall thickness. So that's a circumferential. Now let's look at the axial system. Okay. So as I said before, the ePod and the software and the computers are still always the same. Okay. However, we need the new sensor, which is going to go and send the waves in a different direction. So I'll unplug this sensor. We'll now start to prepare the axial sensor. So this is what the sensor looks like. We again have a transmitter and a receiver. In this case, the receiver is here, transmitter is here. The system then goes and bends in order to handle anywhere from a 4-inch pipe up to flat. And we have so many fingers because it can go and handle different thicknesses. So we use different sections of it are optimized for different thicknesses of pipe. So you can do it all with one sensor. Okay. Then we also have what we call the traction unit. The traction unit is what's going to go and pull this around the pipe so we can go and scan around the pipe. We again, for 6-inch to 16-inch pipe, we have frames which allow you to connect the two together so it can be a fully automated scan. For sizes outside that, it's partially automated. You have to either go and move it manually or you have to help it along. But we're on an 8-inch pipe, so we're going to go and these are 8-inch frames. Then these are the latches which are going to connect the sensor to the traction unit. So this part of the configuration is going to normally be done in your truck or something before you actually get on site, just so you don't lose any of the cable. So that's our axial sensor configured. Next, we need to just put an adapter onto the ePod. These just provide some strain relief so that the cable doesn't pull and damage anything. So QSR is now ready. We now have the traction unit. Again, it's got magnetic wheels so that it doesn't slip on the pipe. The axial unit can be used both for horizontal pipe and for vertical pipe. So here we just clip it in place. Connect up the sensor cable. And then we have a cable that goes from the traction unit to our adapter. This cable is normally about 3 meters long, but it can be made longer if necessary on site. Okay. Let's go back to our software. So once we connect, it should now recognize that we have an axial sensor connected. Okay. And so we can just go and start a scan. And this is now our axial. Now, the other one scanned axially as it sent the wave circumferentially. This one is now sending the waves axially as it now is scanning circumferentially. So after each collection, it's going now moving forward and then going and collecting the next bit. This is really useful for, imagine this being a wall or a deck penetration, something that you can't go and get to and you're trying to go and run through. It's also can be if there's a big clamp support here where you can't go and get the circumferential system to go over because it's going to go and hit the clamp. We're just going to let this collect. We're able to go and, for instance, look at what the tilt is. We have encoders built in, everything so that we can then go and tie up where we're actually going and seeing any reflections to where it actually is on the pipe. And then this allows us to go and get a profile of the loss. You can also see as clock position how we're going along, continuing on. So it goes and samples the data. You can also, in the upper corner here, you can go and see a plot of where it thinks the sensor is, which bit of the sensor is currently active. That's shown in the red as it goes and plots through. Again, we have a similar general display. So the black is the calibration. What in this particular case, it's what's underneath the sensor as it passes from the transmitter to the receiver. We're using that as our calibration thickness. And then whenever we get a reflection that it goes and picks up a loss, it goes and reports what it thinks the remaining wall is. The analysis for the axial is a little bit more manual at the moment than it is for the circumferential, but that's going to be changing as we continue to adapt its algorithm. You can see it continue to go. Wait till it gets past the defect. So we've set up the axial sensor. So the important bit where the sensor actually is less than an inch thick. So it means that we can go and squeeze underneath the pipe, even if it's relatively close to the ground, without having to remove much of the ground. Okay. We're now past the defect, so we can stop the scan. We can look at it. A popular view is what we have here is the polar view. So this is going to go and show you as you go around the pipe where you actually have the issue. And you get a nice, a visual description of that. And so you can go and include that in your report. And yeah, you can go and calculate, use that and combined with the circumferential ideally. So you can get an entire shape and a profile of what your defect looks like in both dimensions. Of course, you can also combine it with our screening one, which is normally done even first, just to go and locate which supports you want to go and really concentrate on. And I would like to thank you for watching, and hopefully you learned a little bit about the QSR scanning system, both the circumferential and the axial, and how they work. Thank you.